Hello there, everybody. Welcome to another MCAT ACE lecture. And in today's lecture, we're going to be tackling the beginning of a multi-part series in general chemistry content, which is stoichiometry. And this is going to be part one, which is going to talk primarily about balancing. So when we talk about balancing equations and those coefficients, those big numbers that get put in front of the various molecules or compounds that we're using in a chemical reaction. And then we're going to take a look at how we can use balanced equations in order to determine moles and moles of another compound. So in other words, let's say that I start with some compound X and it's going to produce some compound Z. I can say if I know how many moles of X I'm going to put in, then I should know how many moles of Z I'm going to get out. So I'll just sort of preface this, and some of the other talks that I gave, you were told that everything we were doing was in preparation for stoichiometry, for this multi-part lecture. So when we were talking about molar masses and we were talking about the concept of moles and Avogadro's number and things like that, that was all sort of a build-up to what we're about to embark on here. So this lecture, part one, is primarily going to focus on balancing equations. So it'll have some math, but it's going to be relatively math light in comparison to what's coming up. So the lecture that's going to come right after this for part two is going to be the limiting reactants, theoretical yield, and percent yield. So this is really the primer for that big lecture that's coming up. So we'll see how long this runs. It might come in at under an hour since we're primarily going to be focused on balancing and it won't be quite as math heavy. But we'll see how much time it takes. So the review here, the basic review of moles and molar mass is the first thing we're going to discuss. This was in some of the previous lectures, so when we discuss this, I'm sort of going to give a very brief overview just as a reminder, because we are going to come back to this later in this lecture, especially when we start doing some of the calculations of, compound X going to compound Z, like I was discussing. Molar mass and the concept of moles will be very important there. Then the main thing, so what are we going to really be focusing on this lecture? How to balance simple equations. So these are the ones that most people are going to be comfortable with. When we talk about simple equations, usually most students can just eyeball them and get a rough estimate as to what numbers they're going to put in front. So then we can go on to how to balance difficult equations, or at least by my standards, what I would call difficult. So what's a difficult equation? A difficult equation is usually an equation that has either a lot of hydrogens or oxygens, and the example I've picked out for this lecture is primarily going to have oxygens. That's the most common one. And they're sort of littered throughout all of the reactants and products, and when you attempt to balance one compound at a time, you will usually find that you keep changing the numbers and you keep changing the numbers and keep changing them, and then most students just get to a point where they give up and they go to the instructor and they say, I have absolutely no idea how to do this. I could do the simple one where it was like this was 2, this was 3, boom, I'm done. And then when I get to this type of equation, I'm just constantly, I can't get the oxygens to balance or the hydrogens to balance, okay? And a side note here, there is such a thing as redox reactions. And when you balance redox reactions, a lot of it will, if it's acidic conditions, you deal with balancing hydrogens, and you have to balance the electrons on each side so that the charge comes out. There's going to be a separate lecture on redox, because there's redox titrations, there's redox reactions, there's a whole set of chemistry, it's called electrochemistry, that deals with redox. So I'm going to kind of put redox in its own learning session. We're really just going to focus on the main non-redox reactions. A lot of reactions are still redox because you're exchanging electrons when you're creating and destroying bonds, but in the classic sense, in the electrochemical sense, where we're balancing electrons on each side, if you're looking for that, this is not what you're going to find in this lecture. Okay. So I have 3 equations picked out. I have a very simple one, I have what I would consider to be a moderate one, and then I have one that I would find, or at least that when I've given it to my students in the past, they find to be very complex, and we're going to walk through how we would tackle that. All right. So then we will talk about finding the moles of a reactant to the moles of a product, and that was, like I was mentioning, the X to Z sort of thing. And then we'll find the grams of product that would actually be produced in that case. And so both of these are very similar to limiting reactants, and we'll talk about that, what that means afterwards. Theoretically, we're not actually going to start, because this session would get way too long if then we break into limiting reactants and calculating that. That's going to be its own session. But in the case of limiting reactants, you really have to determine which reactant would run out first. In today's lecture, the lecture we're looking at here, we're basically just going to say we have excess of whatever compound Y is, and we're only going to focus on how much of compound X will produce compound Z. We're not even going to check to see if compound Y might run out before X. And that's what you would really be doing in the case of a limiting reactant. And then, of course, we will have several review questions along with the general summary of everything that we've gone over here. So let's get started here by discussing just very briefly a basic review of moles and the concept of molar mass. So what I want everybody to remember here is that when we're discussing moles, moles is the central unit in chemistry. So if I would like to go from some compound X, let's actually bring this up here, and we're going to draw, this would be obviously a generic equation. This would not be an actual equation here. But if I have compound X and I add that to compound Y and it produces compound Z, and I say, I'd like to know, I have so many moles of X, let's say I have 2 moles of X, and then I have, it turns out there's 3 moles of Z when I balance the equation. Okay, it's moles. I can find out how many moles of X will create how many moles of Z. But I can't necessarily use a direct gram to gram conversion. So I can find out how many grams of Z would be produced by using a balanced equation and looking at the moles, but the moles are central. I can only turn X into Z mathematically through the pathway of moles. I can't directly say, well, 2 grams of X is going to give me 5 grams of Z. I need to say this many moles of X will give me this many moles of Z. And then once I have moles of Z, I could turn that into grams of Z, and that's where molar mass comes in. So remember, for molar mass, you're talking about taking all of the atoms present, so whatever Z would be, let's say that Z is HCl, then that means I need to go and I need to find the atomic weight or the molar mass off the periodic table for hydrogen, and I would need to find it for chlorine, and then I would add those two up, and whatever value I got, that would be grams per mole, and that would be the molar mass. So I could take moles of Z and turn it into grams of Z using the molar mass. So that's just a very quick refresher as far as, moles and molar mass and what we're talking about there. So remember, a mole is also a predefined unit. So in one of the previous lectures, we talked about how a mole is similar to a dozen. And I could have a dozen pencils, I could have a dozen cats, whatever it might be. That always means 12. So 1 mole of any compound is talking about 6.022 times 10 to the 23rd number of those compounds. It's a set value. All right. Now the grams might change. One thing might be a mole of one compound might be heavier than another. For instance, a mole of cats or a dozen cats, right, would be heavier than a dozen pencils or a mole of pencils. Okay. Now, when we start taking a look at this, that's going to be important because that's why I was saying you can't just go grams to grams, but moles to moles, you can make that conversion. All right. So let's take a look at a very simple equation, because the main thing that we want to start looking at in this lecture is how to balance equations. So the first one that I have is we're going to take iron plus iron chloride, and there are multiple forms. I'm sorry, iron chloride is going to be the product. This is plus chlorine. Okay. Here we go. And then iron chloride is the product. And there are multiple forms of iron chloride because iron can take on multiple charges. So you may come across other examples in different books where you see FeCl2 or something like that. In this case, we're assuming that the iron would be in a +3 oxidation state, and so it would end up with 3 chlorines. So this is what I would call a simple equation to balance. Now, how do I approach balancing when we get to, well, really any equation? But there's certain techniques that get refined when it gets more complicated. I tell my students that you should balance each element individually as you go along, And my general rule is that you should save oxygen for last. Most of the time when you get into combustion reactions, when you get into acidic reactions that have a lot of the multiple oxygens, like a polyoxalate sort of situation, you need to make sure that you save those for the last portion, because if you start trying to balance the oxygens first, it can throw you out of whack. But we don't have oxygens here. This is a simple example. So what I would do is I would say, all right, how many irons do I have on the left? Well, I only see on the reactant side one set of iron, right? Which would come from, there's always an implied 1 that is next to each of these. So if I come over here, I also see 1 iron. So the iron is balanced for the products and the reactants. Both of them have 1 iron. Now this is a tip that can help you out. All right, so listen carefully. When you have an element and that element has the same number on each side before balancing, it means that you will have to have the same coefficient in front of those values. So in other words, because I have 1 iron over here and I have 1 iron over here, the ratio starts as 1 to 1. And so if I'm going to change the number in front of one of them, I must always change the number to the same number in front of the other. And that's the only way that that would work. So if you ever get to a point where you might be struggling in a situation that's more complex than this, and you see a compound that's got the same amount on the left as it does the right, you're going to need the same number in front of that particular compound or atom or whatever it might be, element. Right? So then I look at the chlorines. A lot of people may have already done this in their head by this point, but we're going to walk through it here. Okay? You've got 2 chlorines, and over here you've got 3 chlorines. So what we want is what would be known as a common multiple. We're really looking for the lowest common multiple. And so 2 and 3, the lowest common multiple here would be 6 is what we would come up with. And so what that means is I would need a 2 in front of the 3 chlorines here, and I would want a 3 in front of the 2 chlorines that I have over there. Now this brings up the next important point or tip. Okay, this is less of a tip and more of a rule that you need to make sure you observe. You are never ever permitted to change what's called the subscripts. So that little 2 or this little 3 right here, that is inherent to the chemical substance. If you change that, if I turn around and I say, oh, instead of this being Cl3, I'll make it Cl2, I have now changed the actual identity of the iron chloride. All right? So it is not appropriate to change those subscripts. You're not allowed to do that in balancing. The only thing that you can do is change what's called the coefficients, the large numbers, in front of the here. All right? So when I'm doing this, I need to make sure that when I'm attempting to balance, I leave these subscripts alone. As tempting as it might be in order to, make it balanced, you cannot do that because you've then changed the chemical identity of certain compounds in the reaction. So now I take a look at this and I say, all right, if I've put this number here, I've got 6 because 3 chlorine 2, right? So this would just be chlorine, it's a diatomic element, but I multiply them together. If I have 3 of these compound, then I have a total of 6 chlorine, right? So now I can say, all right, this has become 6, and the chlorine over here has become 6 because 2 times 3. So you always multiply those coefficients by the subscripts. And now I say, let me go back and check the iron. You always need to go back and check, even especially as they get more complicated. When you get to the end, you need to go back and check to see if you did the correct procedure and everything is totally balanced, because things could change. And as you can see here, the iron is 2 and the iron over here is 1, so I need a 2 in front of here. That won't affect anything else because it's just iron, and now it should be balanced. So I take a look, I've got 2 iron on the left, 2 iron on the right, 6 chlorine on the left, 6 chlorine on the right. So this was an example that was, in my opinion, somewhat simple. Okay, so hopefully everybody was okay with that. I would think most students would probably be done that by the time I got through that one. So let's set up a situation that's a little more complicated. So in this case, we're going to do a combustion reaction. And in a combustion reaction, you're going to take an organic fuel, and in this case I'm going to use propane gas. As this compound gets larger in molecular weight, these tend to get more complicated in terms of the balancing. So in order to combust, we're going to need the presence of oxygen. So we have O2. All right. And then most of the time when you're dealing with combustions, you're going to get carbon dioxide and you're going to get water as your products here. So now this one is certainly, this is what I would call a moderate one, because this one is certainly more complicated than the last just by the number of oxygens on each side alone and the number of compounds we have to balance. But I would still rank this as not overly difficult. I would expect students to be able to get through this using the same techniques we used above. So speaking of which, let's go ahead and attempt that. So carbon, if we count up the carbons on the left, we have a total of 3. And if I count up the carbons on the product side, I have a total of 1 because of the carbon dioxide. So what I would need to do is change this to a 3. And now this becomes 3. All right, so this is the way that I do it. You're going to find instructors that have all sorts of different approaches. I tell my students it's one element at a time, and when you balance that element, you get through the balancing portion, then you are permitted to move to the next one. Okay, and I also tell my students move to the next element instead of attempting to go back and then say, oh, did this change the number of carbons over here? Then let me balance that. Oh, did it just change it over here? Because then you go back and forth. So we just balanced carbons. Carbons are done. You move on to the next thing. Remember, I said leave oxygens for last. That's what you normally want to do. So over here, I now say, how many hydrogens do I have? Well, I've got 8 from the propane. And then if I come over to the left here, I have 2. And that is a result of the H2O there. So at this point, I would say, all right, if I have 8 and I have 2, then what I would need in order to balance this out is a 4 in front of the H2O, because now I would have a total of 8 hydrogens on both sides. And I shouldn't need to change what's over on the left here because it already is 8. So I brought those up so that they match one another, right? So now I can come and I can take a look at the oxygens. So I say, how many do I have over on the left? The oxygens on the left totals to 2, and the oxygens on the right are going to total to 4. I'm sorry, no, I'm missing the CO2 there. So I've got 6 from the CO2 plus I've got 4 from the oxygen. So notice it's 6 and 4 because of this oxygen. So 6 plus 4 would be a total of 10 oxygens that are over here. So how would I balance this out? Simple multiplication. I would need 5 in order to get 10. So I'm going to put a 5 for my coefficient in front of here. And now that I've gone through carbon, hydrogen, and oxygen, those are all the elements possible, I need to go back through and make sure everything balances. All right? Always do this double check. You always need to double check. So carbon, all right, I've got 3 on the left. I have 3 on the right. That's good. Hydrogen, I have 8 on the left. I have 8 on the right now after I balance that. So that's good. And then the oxygen, I didn't change anything in this process. I did the oxygen last, so that's good. I've got 10 and I've got 10. So now this is balanced, right? So same process as we used above, just a little bit more in terms of what we have there, okay? But still easy enough to get through without tons of complications. So the next one that I want to bring up here is going to start to get a little bit overwhelming if you were to try it using this method. Now, I would encourage you, in fact I invite you as a challenge, to attempt to balance this without the walkthrough if you can. So if you can, that's fantastic. All right, but I'm going to put it up here. You're welcome to pause the video if you want. And for those that it seems overwhelming or you just want to keep going, please feel free to do so because these can be quite challenging. All right, so this is, wait a minute, put my subscript up there, oxygen 10. Okay, and then we've got H3PO4 plus Cl2O7. So this is the current equation that I would like to balance. So remember, the key here is that I want to do the oxygens last. Now this is going to get a little bit more complicated when we start working through this. So just be patient. You might need to rewind this in order to understand it. All right, so I'll start with the hydrogens. How many hydrogens do I have on the left? I only have one, which is from the HClO4. So I would put one there, and then I have a total of 3 hydrogens over here, right? So if I take a look at that, that should be a simple fix. All I need to do is put a 3 in front of the HClO4. And then I have 3 hydrogens and 3 hydrogens. Good to move on. Don't worry about the fact that this affected the oxygens or anything else right now. So chlorine is next up on the list. Let's look at chlorine. Over here I now have 3 chlorines because of that new coefficient that I put out in front. And if I look at the right hand, the product side, I get a total of 2 chlorines. Right? Now, in order to get 3 and 2 to match, I could say, well, I need a common multiple. But what you have to be careful about here is that this is not a 3. I'm going to put this here. That right there is not a 3. It's the coefficient that's a 3. So as soon as I decide I'm going to change this coefficient to something else, then that means that this is no longer going to be 3, even though I have that there right now. So this is a little more complicated, because if I said, oh, the common multiple is 6, I just need a coefficient of 2 here and a coefficient of 3 here, well, this would become 6, but then if I change this to 2, I only have 2 chlorines. So you're going to bat it back and forth. You're not going to make any progress there. Hopefully people can see what I'm talking about. So in the first example that was easy, the common multiple worked great. We said, hey, I've got 3 chlorines here, 2 here, but because they were inherently built into the subscripts, it was much easier to manipulate them using the coefficients. Here, if I changed the 3, that's coming from the coefficient. So if I want a new coefficient, that automatically is going to take that 3 to a different number before I ever am able to balance it. So what you need to do here is a little bit of simple math, and we're going to involve some fractions. So we say I've got 3 here, and I've got 2 here, so this is the one I need to increase using some sort of coefficient, right? So what I'll do is I'll say, all right, I want the chlorines to equal 3 on this side. I only have 2. So what do I multiply 2 by in order to get 3? It's a basic algebra equation. So 2x equals 3, find x, right? Because what I'm really saying here is, what could I multiply 2 by in order to make that 2 become a 3? And so all we would need to do is algebraically rearrange this, and we find out that x is equal to 3/2 or 1.5. Now, I would encourage you to put the fraction, and that's for the sake of multiplying through the equation, which we're going to do here in a minute. You want to put the fraction and not put 1.5 there. It's just a little bit cleaner, because when you see what's in your denominator, you can multiply through and you can get rid of everything. All right. So I'm going to do this. What I'm going to say is, all right, this can be 3/2 for the moment. But when we get to, because what these coefficients really represent is molar ratios. So we're saying we're going to have 3 moles of HClO4, 1 mole of P4O10, and so on and so forth. When we do balancing, it's okay to temporarily put a fraction of a mole, but usually we deal with moles in whole numbers when it comes to coefficients, okay? So certainly if you're calculating the amount of moles, you could get 0.5 moles of something. That exists. But when we're doing the balancing of equations, we only use whole numbered ratios, and the reason for that is that in certain cases this could lead to a half atom. When you're looking at the general makeup or the ratios, it's not acceptable to have a half of an atom. There's no such thing as a half oxygen or a half chlorine. You either have a chlorine or an oxygen or you don't. And so we have to eliminate these nasty fractions that are here. And if you go through and you look at any normal balanced equation, you're not going to see these hanging around for the final equation when we get through. All right, so 3/2, that's what I would need to put there in order to get the chlorines to balance. And if you think about that, that makes sense, because if I take 3 chlorines over here and then I take 3/2 times 2, that's going to just end up as 3. The 2 will cancel the 2 in the denominator when I'm multiplying, and I end up with 3. Now, in order to get rid of this 3/2, what I'm going to need to do is multiply in order to get rid of this 2. So if I take 3/2 times 2, I'm going to just end up with 3. So I can do that here, but if I'm going to do that to this, I have to do it to everything else. I can't just pick and choose only that compound. If I would like to say, hey, I'm going to do this with a times 2 multiplier, then I need to apply that to the entire set. All right. So take a moment, make sure you have this written down, because I'm going to delete it, and then we're going to rewrite the equation by multiplying everything through by 2, and I'll clean it up here. But just so people know, that means that this is headed towards a 6, because 3 times 2 would be 6. This was initially a 1 that was implied here, so now I'm going to have a 2 here. This would now have a 2 here, because it was an implied 1. And then this would be a 3, because I had the 3 halves, and that was the whole point. I wanted to multiply by 2 to get through that. All right, so one last chance, pause it if you need to write this down, and then I'm going to clean up the equation here. All right, so let me go ahead and bring out my delete box and clear the board, and then I'm going to rewrite this. So the equation at this point should now read 6HClO4, okay, and plus 2 P4O10. That's going to yield 2 H3PO4 plus 3 Cl2O7. Now, I'll just mention here, in case you've seen this from any other sources, sometimes people in these situations, they like to have implied zeros in front of these groups. So instead of the implied 1s, they might have an implied 0, which means when they multiply through, 2 times 0 would still be 0. I like it. What you're doing is you're theoretically waiting until you get to balancing phosphorus and oxygen to put a number there. I don't like to do that because a lot of times I find it confuses students or trips them up. There is an implied 1 there because you can never get to the end and say, well, I just don't need any of these, so we'll leave them out of the equation. This was the original equation we were given. So an implied 1 is what goes there. All right. Now, once we have this set, we have balanced the hydrogens, we have balanced the chlorines at this point, so next up on our list would be the phosphorus. And I say the phosphorus even though oxygen sequentially is here next, because again, look, we have oxygen here, 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 and here. So it's going to be very difficult when I have 4 different areas I can keep changing numbers in to really get the correct ratio in order to come out. The amount of trial and error in that is going to be astronomical as far as your time is concerned. And we all know when you're taking the MCAT, time is something that you need to value. You cannot be spending massive amounts, a half hour just trying out different numbers and seeing if they're working here. So now I go to the phosphorus and I say over here I've got 8 phosphorus. And over here, I'm only going to have 2 phosphorus. So how are we going to get around this one? Well, the same problem is going to present itself here, just like we saw with the chlorines, because this is just 1 phosphorus right here. So if I was to change this and say, oh, well, I just need a 4 in front of this in order to make 8, that's what it looks like from here, right? Just times this by 4. Well, now I have 4 phosphorus, right? And while you could put 8 here, and then you have 8 phosphorus, and you'd have 8 over here, you're going to find that that just screwed up the hydrogens. And if you screw up the hydrogens, you got to put a new number in front of here. And if you put a new number in front of there, you're going to screw up the chlorine, so you got to put a new number in front of here, so on and so forth, right? It's not a good path to go down. So we're going to once again rely on some fraction work here in order to make sense of where we're going to take this equation. So what I do is I say, all right, this is the one that I need to do some number changing with, right? So if this is 8 over here total and this is 2, I need to bring one of these down to the level of the other. So in this case, what I would say is, well, because this one is so high, all right, and then this one only has the 2, we can't change the number in front of here because we know that that's going to create an issue. And we cannot go in and actually change the number down in that phosphorus. So it's going to be difficult if I'm trying to raise this number at all. So what needs to happen is that I'm going to need to bring the 8 down so that this number, this 2, really gives me something that will match a lower number over here. So what do I mean by that? I mean, if I have a total of 8 phosphorus over here, and I would like them to get to 2 phosphorus, I would need to multiply this by what? A brief math check. I would need to multiply this by 1/4, because 8 times 1/4, or a fourth of 8, a quarter of 8, is going to be 2, right? So if I take a 1/4 multiplier to the coefficient that I find up here, I can change it so that the phosphorus will equal on both sides. And this is where students tend to get a little bit lost in terms of how complicated this equation can be. So what I would need to do is I would say 2, okay, not 8, that's the total number that's there. The coefficient is actually a 2. So 2 times 1/4, right, a quarter of 2 is going to be 1/2. So what I'm suggesting is instead of 2, that we're going to change this to 1/2. So let's rewrite down here HClO4. We've got 6 of those. And now what I'm proposing is let's do 1/2 P4O10, because that's going to give us the proper number of phosphorus. And now look, we kept this 6 intact so that the chlorines didn't change on the other side. The hydrogens didn't change on the other side. All I'm changing is the oxygen here, which we've saved for last. Okay, and then once I have the 1/2 there, this is going to yield, I didn't change anything over here. Okay, so just take a look, take a breather for a second, and show yourself. You did not change the hydrogens. I've got 6 of them on the left, right here. Okay, and I also have 6 of them on the right here. So we're good with that. 6 chlorines on the left, 6 chlorines on the right. So far so good, right? The phosphorus, I now have 1/2 of 4, which is going to be how many? 2, right? And then I have 2 phosphorus over here. So we're good to go with that. So what I need to do now is I need to get rid of the fraction again. So I'm going to have to do a ×2 multiplier to this entire set. So what I would end up with is 12 HClO4 plus P4O10. So this is just back to the original, right? And what I need here would be 4 H3PO4 plus 3, I'm sorry, not 3, because we have to do the multiplier, 6 Cl2O7. See, there's a lot of numbers. You can see I keep, as I'm talking, I'm going faster than I'm thinking, and I keep screwing up those coefficients. So it's 12 HClO4, 1 P4O10, and then I've got 4 of the phosphoric acid here, and then I have 6 of the Cl2O7. So this now becomes our new balanced equation, and now we can go ahead and take a look at the oxygens. Right? It's very important that you do the others first, and you'll see why in a second. The reason why is that most of the time the oxygens either balance themselves out or they become very simple to solve at the end. It becomes very obvious once you have the general ratios in place where these need to go. So let's just move that up there. Right? So now for the oxygens, because we just walked through this and showed that we hadn't screwed anything up as far as the balancing of the chlorine, the hydrogen, and the phosphorus, and we just did a ×2 multiplier to everything. So all we did was ramp up and escalate everything to 2 instead of, or twice the amount of what it originally was. So now I take a look at this here and I say, all right, I've got 12 and 4, so that's 48, right? Plus, so this is for the oxygen, right? 12 and 4, 48, plus I have 10 over here, so that's 58 oxygens. Imagine trying to start this off by balancing 58 oxygens on each side. You would be here forever attempting to figure out, one side versus the other. So now let's look at this. I've got 4 and I've got 4, so that's going to be for this side. We'll start out with 16 plus 6 times 7 is 42, and wouldn't you know it, 58 and 58, the oxygens have balanced one another out. This, even though it seems like it took us a while here because I was trying to coach you through it, if you were to do this on the MCAT or some other exam, this is going to be, it may be a little bit long, it may take you a minute or two, but this is going to be the quickest way to get to this instead of just plugging in numbers and attempting to come up on 12, 1, 4, and 6 as you're randomly applying numbers is going to be very difficult to do. And those oxygens are going to drive you out of your mind unless you follow some sort of process to this. So hopefully everybody can see the value in this. And just as a final check, because I always promote final checks, right? We just did the oxygen, but let's check the others just in case, right? Maybe we made an error somewhere. So we've got 12 hydrogens on the left, and on the right I've got 4 times 3, and so I have 12 hydrogens on the right. Chlorines, I've got 12 chlorines on the left, and then on the right I have 6 here times 2. I have 12 chlorines on the right. The phosphorus, if I look here, I've got 4, and then here I have a 4 times 1, so that's 4, and the oxygens we just did, 58 and 58. We are good to go. You've balanced this very difficult equation at this point. So you can see, in comparison to, you know, the iron chloride reaction that we started with, this can ramp up and you know, become something quite difficult if you don't have a procedure that you're following. So don't shy away from using fractional methods if you've spent a minute and it just seems like it's not going anywhere. Attempt to do this method with fractions when you're working with something like this. Okay? So I think that covers balancing the simplistic and the difficult equations using fractions. So what I'm going to do now, I'm going to bring up an example where we'll have a basic equation, and I'm going to ask you guys to balance it, and then we're going to find the moles of a reactant to the moles of a product using this. So that's going to be the next goal here. So give me a second. I'm going to clear this screen off, and I'm going to put the new equation up, and then I'll see if you guys can balance it. Okay, so what I've put up here is an example where we take the substance potassium chlorate, and it's going to undergo a decomposition when we heat it up in order to give potassium chloride, which is a basic salt, and oxygen gas. So what you should try to do here is, I think it should be somewhat simple. Use the skills that we just talked about and balance this equation. I would classify this as a simple equation. And then we will move on to the question, provided hopefully you've been able to balance it. So take a second, pause the video, and then come back after that second or minute where you balance it, and I'll give you the next question and we'll go through that. Alright, so hopefully everybody had a chance to get through this. Without going into too much detail as we're going through this process, right, I would see that I have 1 potassium on the left and 1 on the right, so that should already trigger or cue you that you're going to need the same coefficients in front of the K and the K that we find there. But I have 1 potassium and 1 potassium, so that's good to go. Right? And then I see I have 1 chlorine and 1 chlorine, good to go. And then the oxygens, which I saved for last, I take a look and I see that I've got 3 here and 2 here. Now these are built into the subscript, so this is nice and easy for a sort of a common, lowest common factor that we can find here. So all I would need is a 2 in front of this and a 3 in front of this to make that 6. So now the oxygens are good, but I've balanced this, and now the K and the Cl has a 2, so I would need a 2 in front of this, and there you go, you're all balanced with that equation. So hopefully you worked that out. Shouldn't have taken you more than, I'm going to say 30 seconds to a minute, hopefully, if you were looking at that. Just a little bit of basic mathematics and arithmetic there. So here comes the question. The question that I have is, if we have 26.29 grams of the potassium chlorate, okay, how many moles, and we're going to talk about this in a second here, how many moles of O2 are produced? Okay, so this is getting on the idea of a theoretical yield, which is what we're really going to talk about with limiting reactants next time. So in this case, we only have 1 reactant. I picked out this example on purpose because we don't really have to talk about competing reactants. There is only 1 reactant, so it must be the limiting reactant in this case. And that's the KClO3. So I say if I have 26.29 grams of KClO3, how many moles of O2 can be produced? Now, when I take a look at balanced equations, right, why do we go through all this trouble to balance these equations and make them equal? Well, some people would say the conservation of mass, however many atoms go in, I have to keep that many atoms out, which is very true. You need to make sure you're doing that with your stoichiometry and your balancing. But this is really the multimole requirement or ratio for a given reaction. And the best analogy that I can make to this so that students understand this is that this is just like baking or cooking if you were to have a recipe card, right? So in your recipe card, maybe it says that you would have 3 eggs for a certain baked good and 2 cups of flour, right? And then you would have 1 cup of chocolate chips, and then you would have you get the idea, 1 teaspoon of baking soda, right? And so I take all of this, I mix it together, and then let's say that I could get 12 cookies out of it. So these numbers here, just like a recipe card, these are recipe cards for given reactions, right, when I do this. So it would not be appropriate for me to say, well, I'm going to use, all right, it doesn't translate exactly because there is such a thing as a half a cup of flour, right? You could do that. But this is the general ratio. So if I have 3 eggs and 2 cups of flour, 1 cup of chocolate chips, and 1 teaspoon of baking soda, I mix them together and I say, okay, that gives me 12 cookies. Then I could say, all right, assuming I have excess of all this, let's say that I have 6 eggs, how many cookies could I make? Well, if I had 6 eggs, then I could do 2 batches here because it's 3 eggs per batch, so I could get a total of 24 cookies, all right? So this is the same idea here. It's saying for every 2 potassium chlorate that you put into your recipe, and that's what it calls for 2 of them, I will get 3 O2 gas molecules out, right? Every 2 KClO3s I put in, I will get 3 O2s out. So it's just like the cookie yield in the recipe card. What I'm really looking at is a chemical recipe for the decomposition of potassium chlorate. And so that is a very good analogy or way to frame balancing equations and then how they can be applied here. So this, when I said, oh, I've got 6 eggs, so the recipe normally calls for 2, this right here, I'm telling you, I have 26.29 grams of this compound, so how much of the O2 could I get? And I need to go to my recipe card if I'm going to be able to find out how much that how much I can get. So, in order to solve this, we're going to start with what's known, which is that we have 26.29 grams of KClO3, right? And when I take a look at this, I usually like to set this up as canceling tables so people can see the units. What I'm going to need here is the molar mass of KClO3 in grams, and we always know that the molar mass is for every 1 mole of the compound. So 1 mole of KClO3, right, is going to be how many grams? That's the question. So what we would need at this point, and you might want to pause this and pull one out if you want to work along, is a periodic table, because we're going to need to find the molar mass of KClO3. So I'm going to continue here, but feel free to go pause this and grab a periodic table if you wanted to do this alongside. Right? So based on the periodic table that I'm utilizing, I have 1 potassium, and potassium comes in at 39.10. I have a chlorine, and the chlorine comes in at 35.45. These numbers are coming from the periodic table. And then I have an oxygen. That oxygen comes in rounded because it's 15.999 on the one I have at 16.00. Notice I'm keeping 2 decimal points on each of these. All right, now there's 3 oxygens in the potassium chlorate, so I need to make sure that I multiply this by 3. All right, and then if I sum all of that up, what I got when I did that was 122.55 grams per mole. So that is the molar mass of the potassium chlorate. So down here, I would put in 122.55 because it's that many grams of potassium chlorate that will make up 1 mole of potassium chlorate. All right. Now here's where this is actually, in my opinion, the easiest step, but this is where a lot of students get tripped up. They'll take that and then they'll assume that now that we're in moles, we can automatically figure out that that's the moles of O2 that are produced. And that's not correct. We need to look at our recipe card. Our recipe card states that we have 2 moles of KClO3 to every 3 moles of O2 that's produced. Now if I solve this 3/2 multiplier will give me the correct answer. I cannot just stop at the step before that. So take a look at what I'm doing here. I'm turning the grams of potassium chlorate, I'm going to cancel this, into moles of potassium chloride. Then and only then can I switch it into moles of oxygen, because I don't know a gram to gram ratio of oxygen to potassium chlorate. What I do know is that for every 2 moles of potassium chlorate, I get 3 moles of O2 based on those coefficients. And so what I work with here, I say, all right, moles of potassium chlorate will cancel out, and then I'm going to have the 3/2 here, right? So if I run through and I multiply and divide all of this, I'm going to keep 4 significant figures because that's the original value that was given to me. So I run through all of this, and the answer that I came up with when I did this was 0.3218 moles of O2. All right, so this is how you would figure out, if I'm given a certain amount of my reactant, how much of the product could I potentially make. And again, this is not necessarily figuring out which reactant's going to run out first when we talk about limiting reactants. That'll be all for next lecture, but we are going to talk about the theory behind that in just a moment here. All right, so that is how we would solve for the moles of that. Now, if I wanted grams of the O2, I could move on from the moles of O2, and all I would need would be the molar mass of O2. So I could take this value here, and I could say, let me move down so I have a little more room here, okay? Because you might come across a question where it says how many grams of O2 could be produced. You would need to take the steps that I just showed you in order to get moles of O2. And then once you have moles of O2, all you need is the molar mass of O2 to go into grams. So you would say, I want to cancel moles, so for every 1 mole of O2, I know that, well, O2 is going to be 2 oxygens, so 16 plus 16 is 32. So if I took 32 grams of O2 and I multiply that times the moles, then I would get the grams, and that turns out to be 10.30 grams of O2. Okay, so again, I could take it a step further and I could figure out the grams of O2. I don't have to stop at the moles, but I can't jump from grams directly to grams. I have to go through the molar ratio, the 3 to 2 moles there, before I could start talking about the grams of O2 that would be produced. So again, this is very important when we start getting to limiting reactants and theoretical yields and percent yields and all that kind of stuff, which will be next lecture. All right. So coming back up to our list here, we've talked about finding the grams of the product produced and the moles for a reactant to product ratio. So I just wanted to talk for a moment about the theory of limiting reactants. This is going to be a very brief discussion because I'm really saving that content for the next lecture. So let's clear the board here, and I just want to give you a very brief example in terms of limiting reactants. And in fact, for right now, so it's not too confusing, I am going to keep this generic. So remember when we started with X and Y, and then we came over here and we had Z, right? So if I wanted to, let's say that the balancing here is 3, 7, whatever this is, and this is 4, okay? So if I wanted to come and work with this, and I said, the question becomes, which is the limiting reactant, meaning which reactant will run out first, X or Y? And a lot of students here will get confused and they'll say, oh, well, there's only 3X and there's 7Y, so you run out of X first. Well, not necessarily, okay? And then a lot of students will also get confused, and let's say that I have 10 grams of X and I have, 18 grams of Y, and they say, oh, 10 grams will run out before 18 grams. Again, you need to do it on a molar basis, all right? So what we would do in order to solve this is we would take the grams of X and we would take the grams of Y, and then we would convert that into moles. So I would say, oops, it's going to be on top. I would say the molar mass of X, so grams of X equals 1 mole of X, right? And then on top of that, I would say, all right, so now if I want to find out how much Z it could produce, I would say, all right, so it's going to be 3 moles of X to 4 moles of Z, right? And then we would say that that's going to be moles of Z that could be produced. And then I do the same thing for Y, because I have 2 of these here. So now I say, what is Y's molar mass? So the grams of Y for every 1 mole of whatever Y is. And then I would look at this ratio and I would say I've got 7 moles of Y for every 4 moles of Z. And when I do that, I would also get moles of Z. So these are 2 theoretical values. This is how much Z could X produce given the amount, and this is how much Z could Y produce given the amount. And the lower value, so whichever one could produce a lesser amount of Z, would be the limiting reactant. You would say, oh, this is my limiting reactant because I can produce a lesser amount of Z than I could with the other reactant. And then you would expect that reactant to run out first. Okay, so that's limiting reactants. The math behind that is more complicated than what we just did. Not necessarily more complicated. You're doing it twice over and then comparing the values. Okay, but we're going to save that for a different time and table that. So I'm going to put some questions up here, mostly revolving around balancing, but we'll certainly have a little bit of math based on what we did. And then we will do a review, a summary, especially in regards to balancing equations. And then we'll be all set with this. So give me a second to clear the board and put the questions up here. Okay, everybody, here are the questions that we are going to be working with. So kind of in the similar style to an MCAT, sometimes you will come across, in fact it's very common, to come across a bundled set of questions for one specific equation, you know, organic mechanism, balancing, whatever. And so that's exactly what I did here. And it says, you know, sort of like a passage. The following questions are based on the equations shown below. So imagine that this is your passage. So they give you this, and then you're going to have 3 questions you need to answer based off of the content that they've shown you. And this is going to kind of scaffold. So, you know, getting the correct answer to the first one is going to be important for the second, and so on and so forth. So if I take a look at this, all right, what I have here is sodium phosphate, and that PO4 is treated as a group. It's called a polyatomic anion. I wanted to give you guys something a little bit different here that we're going to work with. Plus magnesium chloride goes to sodium chloride and magnesium phosphate. And I've given you the proper structures there, but this is an unbalanced equation. So here we go. Number 1, based on the equation above, what is the molar ratio of magnesium chloride to sodium chloride? So the only way you're going to find that is by proper balancing, and you've got a couple of answers there. Okay. Number 2, this is assuming you have your balanced equation. How many grams of sodium chloride could be produced using 10 grams of magnesium chloride? Assume excess sodium phosphate. So in other words, take a look up here. I've got 2 reactants. So in the case of limiting reactant, this question could change after the next lecture. But for right now, we have to assume, since we didn't really talk about it in detail, that one of the reactants is in excess. So I'm already telling you, you'll run out of magnesium chloride first. You have 10 grams of it. So how much of the sodium chloride could be produced on a gram scale potentially if I use up all 10 grams of that magnesium chloride? What would be the theoretical outcome in terms of grams? And then number 3, similar, but this is actually going to tap into one of the previous lectures where we talked about atoms and molecules. How many sodium atoms, all right, sodium atoms, you could call them ions if they're in solution, how many sodium atoms can be produced using 10 grams of magnesium chloride? So similar type of question, but different in terms of what it wants. Up here, we're looking in number 2 for how many grams of sodium chloride can be produced. And then in number 3, how many sodium atoms, the individual atoms of Na, can be produced using 10 grams of magnesium chloride. Again, assume that you have excess sodium phosphate. So once you're out of magnesium chloride, the rest of that sodium phosphate would not react there. So we're not really assuming, oh, well, if you have excess sodium phosphate, you could have infinite number of sodium ions. We're simply saying, once you use up all the magnesium chloride on the product side, how many sodium atoms could you obtain? And you've got a couple of options there. So take some time to work through these. The first, well, all of them are going to involve math, but especially the last two, right? And then once you've had a chance to work through these, I would encourage you to then unpause the video and we can take a look at this together. Just one tip. When I balance the phosphates, the PO4, see how it's bundled with a 2 here on the product side? It's easier to treat these as entire groups. So when you're going to balance, because there's no other place for oxygens here, when you're going to balance the phosphorus and the oxygen, balance them as a group. So balance the PO4 as a PO4 group, and that'll keep the ratios of phosphorus and oxygen the same. It'll make it a little bit easier on you. So that's just a tip, and then I'll show you as we go through here. So good luck with these, and then I will see you guys in a moment for the walkthrough. Alright, so hopefully everybody had a chance to work with these. If you got stuck, that's fine. Certainly come to the walkthrough and we will figure out what is going on here together. So, the first thing we need to do, and this is a very good habit to get into whenever you're dealing with any type of question like this that gives an unbalanced equation, it should be a gut reaction. Balance the equation, then I'll go do math. Balance the equation. That's what you want to focus on, balancing the equation. So, if I take a look here, I have limited space, okay, but I'm going to try to work through this with you guys. So, the Na, the sodium on the left is 3, and then on the right, I only have one of them, right? So, I can put a 3 here, and that will temporarily solve the sodium problem that I have. So, I could move on. I can treat the whole phosphorus, but because that has oxygen, I'm actually going to come back to the phosphorus in a minute. Or I'm sorry, the phosphate. I'm going to come back to the phosphate in a minute because I like to save my oxygens for last. And I'll treat this whole thing as a group when I'm attempting to balance it. So let me come over here. Magnesium. I've got one magnesium on the left. And then on the right, I have 3. So similar to the sodium, but in reverse here. So if I have 3 there, I would like a 3 in front of here in order to solve that issue. So then I go and I say the chlorines over here. So the chlorines, all right, if I look at these chlorines over here, I've got 6. That's 3 times 2 is where that's coming from. So I've got 6 chlorines on this side. And then if I go to the product side, I only have 3 of them. So I'm going to need to bump this up to a 6 in order to make that work. Now I have to keep in mind that may have just disturbed, in fact it did disturb the sodiums, but don't go back to that just yet. We'll look at the phosphate. You run through all of your sets once, then you go back and you do your double check. All right. So now I have 6 chlorines on this side, so my chlorines are good to go. Okay. So now the phosphate, and again, I'm going to treat this as a group when I'm trying to balance it. So I'm going to say I have one, running out of room here, but I have one PO4 group, one phosphate group over on the left, and I have 2 phosphate groups over on the right. Okay? So much easier because the ratios here, you can't do this in like the complicated equation we did earlier because you have oxygens on multiple substances. They're not grouped in nice set clusters like this where it's always a PO4 and a PO4, right? So I can do that in a case like this, and it does make life easier than trying to separate out the phosphorus and then go on to the oxygen. So what I'm going to do here is I'm going to say I have 2 of these over here, and so what I would need is a 2 to be applied here. And notice that this 2 gets distributed to the phosphorus, and that would mean I have 8 oxygens here. All right, so I need to distribute a large 2 because I can't change this. I'm not permitted to do this. That's changing and adding a subscript. So I put a large 2 in front, and then this will be distributed to that whole chunk there, and that's perfectly acceptable. All right, so 2. And now those are even. So I go back through, and now only at the end should I start taking a look at everything again. So do the sodiums match. Here I have 6 based on the 2 for the coefficient and then the 3 down there. So I have 6 sodium, right? I've got 6 sodium on the right side, on the product side. Magnesium, I've now got 3 over here on the left, and I have 3 on the right. So that works fine. Chlorine, I have 6 on the left, I have 6 on the right. When this changed, that coefficient went from a 3 to a 6. So that's good, and we just got through with the phosphates, so they still remain at 2. Everything is in place here. Now, The question, now that we took all that time to balance, the question is, based on the equation above, what is the molar ratio of magnesium chloride to sodium chloride? Here's magnesium chloride. Here's sodium chloride. We have a 3:6 ratio. Well, if you notice, none of the answers have that, and that's because we can reduce the general ratio here, right? And that general ratio can be reduced as a 1:2 if I'm doing a common denominator sort of thing, dividing through. 1:2 is the proper ratio here, because 3/6 is the same thing as 1/2. So the correct answer here should be A if you got through and you balanced this entire equation. All right, now these balanced equations, you want to have this handy because you're going to need that to solve for 2 and 3. You would also need a periodic table in order to do this next part. All right, so number 2, how many grams of sodium chloride can be produced using 10 grams of magnesium chloride? That's the question here, assuming excess sodium phosphate. So what I would need to do, I'm going to set this up, I'm going to try to squeeze all of the math in here to the right of these answers and show you what's going on. I may sort of abbreviate some of the units to make sure we have enough space, right? So I have 10 grams of the magnesium chloride, right? And so if I look up the molar mass by adding magnesium and 2 chlorines, I'm going to find you should have somewhere around 95.21 grams of magnesium chloride for every 1 mole of magnesium chloride. Right? So then I keep going. Now, I'm going to squeeze this in up here. I'm going to give myself a little more room, just because I want to make sure everybody sees where this gets canceled out here. All right? So that's for 1 mole of magnesium chloride. So I then would go up to my equation. I'm looking for sodium chloride. How much sodium chloride can I produce? Well, this is all the same sort of question here, right? We looked at this ratio first. So we have magnesium and sodium chloride. It is a 3:6 ratio here. Now, where does the 3 go and where does the 6 go? Well, I want to get rid of moles of what? Magnesium chloride. And I'd like to turn those into moles of what? Sodium chloride. And so if I look at the numbers up here, I've got 6 sodium chloride to 3 magnesium chloride. So 3, 6, or some people will put 2 and 1, which is completely fine here because when you reduce down, just like the 1:2 ratio, that's going to be the same sort of thing there. Right? But I'm just showing where this comes from in the equation so nobody's lost and says, I don't see a 1 and 2 next to those values up there. Everybody should see the 3 right here and the 6 that we had up here. Okay, so then it's asking for grams. Right now we have moles. So in order to complete this, we would need the molar mass of sodium chloride back to the periodic table, add up sodium and chlorine, and what you should get is 58.44, or somewhere around there, grams, okay, of sodium chloride for every 1 mole of sodium chloride. So grams of magnesium chloride cancel grams of magnesium chloride. Moles of magnesium chloride cancel moles of magnesium chloride. Moles of sodium chloride cancel moles of sodium chloride. I'm left with grams of sodium chloride, which is exactly what this was asking for. Okay, if you plugged all of this into your calculator, you should have found 12.28 grams as the answer, and here you go. That would be C as the correct answer here. For these questions, unless something is very obvious and smacks you in the face, okay, you should just jump right into the math. I know a lot of times there's techniques for process of elimination. In some cases that works, and we've seen that in certain videos. In this case, I wouldn't suggest it. I don't see anything that's astronomically high or low. They all seem like reasonable numbers. And so I need to go through and just get hammering on the math as quickly as possible so I can get that proper number out, okay? Another piece of advice, and it's up to you how you want to use your time. I do this even as an instructor. I double check my calculations. So I set all this up. I plug it into my calculator once. I'm human. I make errors. I put the wrong number. I reverse something. I leave an exponent out. I always run through it again, and I make sure I get the same number out twice. And the number has to be somewhat logical, right? If I start with 10 grams of the magnesium chloride, I shouldn't end up with 350,000 grams of the other. That wouldn't make sense even on that mole-to-mole ratio that I should be getting such a large amount back out with the conservation of mass. Okay, so how many sodium atoms can be produced using 10 grams? So this is going to have a very similar setup to start. I would say that I'm going to have 10 grams of the magnesium chloride. Okay, and then that's going to go to moles of magnesium chloride. Again, similar setup to above, so 1 mole magnesium chloride. Okay, now I would still need the same ratio here, mole to mole ratio, because I'm looking for sodium atoms in the product and they appear in the sodium chloride. And so I still want to utilize that 6:3 ratio, because what I need in order to get the atoms of sodium would be the molecules of sodium chloride, and to get molecules of sodium chloride I need moles of sodium chloride. All right, so I'm going to have 6 moles of the NaCl to 3 mole of the magnesium chloride. Now I will probably run low on room here. Right? So what comes after this, now that I have moles of sodium chloride, is I need to find the molecules of sodium chloride. So for every 1 mole of the NaCl, I need 6.022 times 10 to the 23rd, and the unit I would write out here would be molecules of NaCl, okay? And so the moles of NaCl cancel, it's the molecules of NaCl now. Now what you would do, if you run through all of that, you see that you get 1.265 times 10 to the 23rd molecules of NaCl. That's what we have right now. Now it turns out that there's 1 sodium in every molecule of NaCl, so this number would be the correct answer. But you have to be careful in a situation if this for some reason said, for instance, that it was Na2Cl, that wouldn't be correct. But if that was the case, okay, then you would need to multiply this value times 2, because there would be 2 sodium atoms in every 1 molecule of NaCl. So just keep that in mind. As, again, this is not a proper compound, but keep that in mind for if you come across something like that, you need to keep track of those atoms. So the correct answer is D. We would have 1.265 times 10 to the 23rd. Again, no answer really smacks us in the face and stands out here, so we would argue that we need to go straight to the math. All right, so let me clear this, and then we're going to do a brief review, and you guys will be all set for this content. Okay, everybody, so if you have any issues with this, I would suggest going back over and watching the way that we balance these equations. Practice the practice problems again. This is a general overview for what we learned and some tips and things to keep you on the correct path. Simple equations usually can be easily balanced 1 atom at a time. So we just start, we say I've got 1 iron over here, 1 iron over here, we move to the next, and so on and so forth. As a general tip, and this is for complex as well as simple equations, if you find the same number of the element on each side, and it only appears once, okay, then that means that you have the same coefficient that needs to be there. So there were a few examples where we saw that, where we said, oh, well, if I only have 1 of element X on this side, then I only have 1 on this side. Whatever the final coefficient is, they have to be equal to one another in order to balance that out. So that's just a good check for yourself, okay? For complex equations, save the oxygen for last. Don't try to tackle that oxygen first. Utilize fractions if you're constantly rebalancing. You're welcome to try it without fractions, but if you see that you're going back and you're rebalancing and rebalancing after 2 minutes, you need to get out of there and you need to attempt to do a fraction in order to put it all the way through. And I would honestly suggest trying and going for that method first. But it's what you're comfortable with. Multiply, if you're going to do the fractions, multiply the equation through by the denominator in order to eliminate fractions. So in other words, our our reactions, they might be organic chemistry, but our reactions should not have partial fractions of a mole when we start dealing with the whole molecules that we're starting to balance there. So you need to make sure you multiply everything through by the denominator and apply that in that case. Okay. So balanced equations are like recipe cards. They tell you the amount in to the amount out. So it says the reactants, those are the amounts in, I follow that recipe, I get a certain amount out, and that's my balanced equation. That's useful for converting. So we learned that we can convert grams of a reactant into moles using molar mass. We can then convert the moles of one reactant into the moles of a product. That was sort of the novel thing that we took a look at this time. We already sort of knew, okay, molar mass, I can turn grams into moles from previous lessons. But this time we said, I can now take moles of a reactant and find out the moles of a product instead of just stopping at the moles of reactant or atoms of reactant. I can find out how much it's going to give me after it goes through a reaction. And that is from the ratio. That's only obtainable from the balanced equation. So convert moles of reactant to moles of product, you need the ratio of a balanced equation there. And then finally, you can convert moles of the product into grams. That's sort of the reverse of what we started with when we were converting grams into moles for the reactant. You can take the moles of potential product, turn it into grams using the molar mass, and then you can find the grams there. You could also do this like the third question we looked at with atoms or molecules or anything like that. So hopefully everybody found this lesson useful. So thank you for watching this portion of the MCAT ACE lecture on stoichiometry, and we will see everybody for part 2.